So let's look at energy use in walking and running now. Now this is not something a future leader probably needs to know about, unless they're trying to get fit and get thinner, but it's kind of interesting that most people don't really understand where your energy goes when you walk or run. We all walk or run a lot every day, and where is the energy going? I've asked many seminars and classes this question in the past, and very few people, including the professors, can answer. Now, you might think it's the same sort of calculation as we've seen for like a bicycle, so it's maybe wind resistance. But walking speed is pretty slow, maybe 4 kilometers an hour. So if you do the calculation, the energy for wind resistance is absolutely tiny. It can make a difference in the Olympics if you're trying to sprint, whether you do the 100 meters in 9.8 or 9.7 seconds, but for the average person it makes almost no difference. How about friction? Well, if someone was dragging you along the floor, then there'd be a lot of work from friction, but you're not, you're walking. Your feet are not sliding on the floor, so there's actually no friction loss. There's also no rolling resistance because you're not rolling, you don't have wheels. If animals could evolve wheels, that would probably make them more efficient, but there are good biological reasons why it's hard. It's very hard to run bloodstream and nerves into wheels. I suppose you could have an entire animal that rolls. That might be a good thing on some alien planet and very energy efficient, but most animals it's not an option. So where does the energy go? We know there is energy because we can put an oxygen mask on someone walking on a treadmill, and it turns out they use about 20 megajoules per 100 kilometers. Not a lot, but you double what you use on a bicycle. Now, to understand where the energy is going, we have to look at the gait, what you do when you walk. So here is a stick figure diagram of somebody walking. And you can see they start off with 1 foot forward on the ground. The definition of walking is that you have at least 1 foot on the ground at all times. That is the difference between walking and running. For in running, you're actually going to be in the air, have no feet on the ground some of the time, as we'll see. So you put 1 foot down at the front, and then that stays on the ground while your body moves over it. It then stays on the ground as it goes back. Meanwhile, you've brought your other foot forward in the air, and then you put your second foot down on the ground, lift up your back foot, and bring it back to the front again. So you can see there's at least a couple of things that you're using energy on. One is each foot has to be picked up and moved back to the front. So that's going to take some sort of kinetic and potential energy to accelerate it up and put it down on the ground. The other thing is that you can see that you put your foot down and then your body moves over it, and that generally causes your body to get higher. So you can see the person is getting higher here, then lower, then higher, and then lower. So your entire center of mass is moving up and down for every stride you take. And you can actually see this if you go walking and look at the scenery around you. You'll see that during every step your eye level just does go up and down. You might wonder why you don't bend your legs as you go forward to keep your body the same, but if you're doing that you have to straighten them at the end, and you're applying a force over a distance, so there'll be work from that as well. So in fact it's most energy efficient to have what's called an inverted pendulum. So the basic idea is you put your leg down and then it stays at roughly a fixed length, and that means your body has to move up and down as it swivels underneath you. And we can use this fact to calculate the energy required. So let's imagine that your legs is about angled 25 degrees forward when you put it down on the ground and 25 degrees backwards. So it's swiveling over plus or minus 25 degrees. A typical leg length for a man would be about 0.8 of a meter. So using a bit of trigonometry, you can see that there's going to be a difference in height of whatever's above the leg of about 7 centimeters, L1 minus cosine 25 degrees. So your body is moving up and down your centre of mass by about 7 centimeters. Now you can argue that it will depend on great details of your gait, but it's going to be roughly that. So what's the energy per step? This is now a potential energy. You're raising your mass, or at least some of it, by 7 centimeters, which requires about 50 joules. So mg times the height difference, mgh. Now if your stride length like mine is about 0.7 meters, that means you're going to have about 143,000 steps per 100 kilometers. So if you've got 50 megajoules per step, 143,000 steps, that means multiply them together, you get about 7 megajoules per 100 kilometers of walking. But remember that human muscles are only about 20% efficient at converting food into mechanical energy, so the true energy use is about 7 over 0.2, so about 35 megajoules per 100 kilometers, which is actually a bit too high. That's more than the actual measured value, which is about 20. And the reason is that a lot of evolution has gone into making the walking gait in humans, and in fact other animals, extremely efficient. So what happens is, your body's going up and down every step. As it goes up and falls down the far side, it acquires some kinetic energy, which then helps carry you up the next step. You're actually using a natural pendulum motion to bring your legs forward. You don't need energy to bring each leg forward. The legs would swing backwards and forwards with a very natural pendulum motion, and you're going at that sort of pace. And this is actually what sets the pace of human walking. It's to match that natural pendulum. And so you can reclaim a lot of the energy of all these gains in height, as the kinetic energy helps power you up the next step. And it turns out this is indeed the case for humans, and that's why it's only about half of what you naively calculate. Rather than 35 megajoules, it's only about 20 megajoules per 100 kilometers. And many other animals do the same things. Kangaroos, for example, every time they bounce, there are elastomers in their legs that reclaim a lot of the energy of each bounce and put it into the next bounce. So a lot of evolution has gone into making this locomotion extremely efficient. How about running? Well, the definition of running is it's where your feet leave the ground. Why would you do this? Well, if you're trying to walk really quickly, that means you're going to be up and down more and more times, and so that's going to use more and more energy. So at some point, it becomes more efficient to, instead of taking lots of fast steps, to take a few bigger steps. And the way you get a bigger step length is by leaping into the air and flying some sort of distance before your foot comes down again. This means each individual step is going to require more energy because you have to push harder to actually fly through the air. But you don't need so many steps per given number of kilometers. So in fact, it turns out that when you're going more than about 8 kilometers per hour, running is more energy efficient than walking. How do you calculate the energy from this? Well, it's primarily just the change in your height, mgh, potential energy. You can work out, if you go a particular distance with each leap, what your vertical speed must be, which turns into potential energy and then comes back into a speed. And this is indeed how you work out the energy from running.